I got it.
Go ahead.
Number one.
Less mass, greater penetrating power. Is the first part true? Is he right with that?
Yes.
What's the symbol for beta, or the notation? What would I...
B, like a little B minus.
Right, but the other one.
I don't know.
Not the B minus, the other notation. 0 over negative 1e. That's beta. What's alpha? 4 over 2he. Which number is the mass, the top or the bottom?
Top.
Top. 4 is the mass, 0 is the mass. So he's right. Less mass, so it's 1 or 2 for sure. Now, if this particle is smaller than this one, which it is significantly, will it have a greater penetrating power? Yes. So good job. If it's smaller, it will penetrate easier. Alpha, piece of paper blocks that. Beta will go through paper, but some sort of foil will stop beta, most of it. So, and then gamma, remember, is the greatest penetrating power out of the 3 of them. So, very good. Very common Regents question. Very, very common. Okay? The next question I wanted to show you, we didn't get to it yesterday in our notes, so I'll skip it, but there's another one. So number 30, we'll talk about, if we have time later. If not, I'll show you tomorrow. And 2 people, well, 1 person, I guess, voluntarily came to get help on the quiz. The other just kind of got roped in because he was in here. They got some points back on their quiz. So remember I told you that. You only have till tomorrow. So that quiz I gave you back, you want to fix it, come see me because I didn't give you the answers. So you have to work on it with me, try and fix it. Alright, so number 50s. And it helped their grades out quite a bit.
I'm coming in today.
Didn't it, Zach?
Indeed.
Jake?
My average up like 6 points.
There you go, because we haven't had enough quizzes yet.
Well,
So we will have 2 more quizzes before the end of the quarter.
I'm gonna come in. You have 9th period study hall, don't you? Or 8th period?
8th period, yep.
Yeah, I'll come in. That's how much math you do.
Number 50, what do you guys think? Which equation represents natural transmutation? And then I'm going to follow that up with which one is artificial. So you should be able to pick out which one is natural decay, natural transmutation, which one is artificial transmutation. What do you guys think? Go ahead.
3.
What about 3? What is natural and artificial?
What's so natural about it?
No. So you think 3 is the answer to the question, to
Natural.
this question right here.
Yes.
Try again. Do you know what transmutation means?
It's 4 then.
Do you know what transmutation means? Can you define that? If I say, what's the definition of transmutation?
Yeah, it's one element changes to a completely different.
Yeah, I didn't do mine yet, but
That's
I still
not
have
what I
time.
meant. I didn't say that. Tough enough.
One element turns into a completely new element. So
Yeah.
3 and 4 are definitely wrong. Why?
Yeah, nah, so what happens is...
No, don't do your dance here. Tell me why these are not transmutation.
Oh, because they don't change.
Right, S-S-N-A-N-A. So I'm glad you got it wrong that way because I was going to teach you
Because
that.
I didn't know what transmutation meant.
Right,
That would be
that's
the
why
same
we're
thing
going
as
over
yes,
this.
Wait, what does transmutation mean?
Oh, one element changes to a completely different element. Naturally.
Yeah. Yes. Good. So we all go to transmutation now, I hope?
Yeah.
Because otherwise you can't get this right. So now, which one, because both of these, right, 1 and 2, turn into new elements on the product side. So carbon turns into nitrogen, B and HE turn into N and N, right? So these are transmutations. So, Jenny, which one is natural, which one is artificial?
Number 2 is natural.
Very good. This is natural because carbon does this on its own, decaying into these 2, transmutating into nitrogen, giving off this. What's that? Xavier knows. No, this. What is that particle? Alpha, beta, gamma. Beta, good. So this gives off beta particles, turns into nitrogen. That's natural decay. Number 1 is artificial. How do you know, Kristen? How do we know this is artificial?
Because it hits it with the alpha.
There's 2 particles, right, it's with an alpha particle. So you have 2 particles. Scientists take that alpha particle, smash it into the nucleus of boron. It gives off a neutron and transmutates into nitrogen. So artificial, natural, right? So this is a real common question. You'll probably see one this year. So for the regents, we got to get this straight. You are going to have a quiz on nuclear chem, which is important for your grade, but ultimately we're getting ready for that test. So you got to make sure we know the difference between natural and artificial.
When is that quiz?
Next week. I don't know when. Tuesday sounds good. Wednesday.
Thursday sounds good to me.
Oh, money. Bree brought me in money. Someone else in here owes me money. I have the list right here. Figure and
Sarah, because you have the pen.
yes, you're right, Sarah. All right, I have a couple videos to show you, but not right now. Go to your notes first, then we'll watch the videos. We left off talking about what?
Fission and fusion.
Fission and fusion, right. Bree, can you hit the middle switch, please? So, I think the last thing we wrote was the reaction for fission.
I think it's 235 with 92 JPU.
Okay. So fission is when you take uranium-235 and you hit it with a neutron and it breaks into barium and krypton and it gives off 3 more neutrons. One thing I didn't have yesterday that we need to add now is energy. Okay? And I gave you all the numbers yesterday, so bear with me here. 142 and 91. So 142, 91. Are you guys good with the lights here? Do we need more light? Anyone besides Ryan? Are you good? You guys good? Okay. Barium is 56. Krypton is 36. And 92 for you. Okay, so nuclear fission. This occurs in nuclear power plants. This slow neutron, we say slow because it's just not moving super fast. Still pretty fast. Hits uranium. What's fission mean? What's a fissure? Or a fissure? Fissure is how people say it. Fissure. What's a fissure?
They're like these little
It's
weeds.
a drop in the first.
It's like a crack in the earth, basically. So fission is splitting, kind of like a crack is splitting the earth. So fission means you're splitting. What are we splitting? Uranium. What is it splitting into?
Splitting into whatever that is.
Barium and krypton, right. So you take one big nucleus and split it into 2 smaller. These 2 are smaller than that. Okay, think of anything that you cut in half. Take this desk, if we cut it in half, we'd have 2 pieces that are smaller than the whole desk together, right? So these 2 pieces are smaller. That's fission. I'm not going to define it. That's what fission is. Because I think the example is better than writing a definition. So this is what creates electricity in nuclear power plants. One video today is to show you that. It's pretty cool. I think it's pretty cool and it's relevant, right? I mean, there's nuclear power plants all over the place. You should have an idea of how they work. Sadly, you don't need to know for the regents, but I like to teach it anyway. I think it's appropriate. So, but you do need to know this for the regents. Fission reaction, here it is. There's another one I'll tell you in a second. But first, with a couple stars, this is real important. This is going to explain why nuclear power is so dangerous. All right, or nuclear weapons. So the mass of the products in real life, I'm going to actually write that, in real life, because on paper this doesn't show on paper, but in real life. The mass of the products in real life are less than the mass of the reactants. Question is, why and how is that possible? Because we learned in the beginning of the year, there's a law of conservation of mass. And that applies to all chemical reactions. In other words, the mass of your reactants should equal the mass of the products. If you do the math, 236, it adds up to 236. So on paper, it looks like it does work, but in real life, the mass of these here are slightly lower or less than the mass than you started with. Why? I'll give you the first answer, because this is not a chemical reaction. What is this? We're not talking about chemical reactions anymore. What are we talking about? What's this unit called? Nuclear chemistry. Nuclear reactions are very different because you're taking the nucleus and messing with it. Protons, neutrons are changing. So it's a whole new ballgame. Different totally different set of rules here. So that's the first why, but that's not the why you need to know. Any ideas? Why the mass of the reactants are greater than the mass of the products? Where's the mass go?
Energy.
I can't believe you got that right.
I was gonna say it.
Very good. Why? Because mass is converted to energy. Very good, Ryan. Mass is converted to energy. And underline that or circle that. Do something. That's real important. So the reason an atomic bomb is so damaging and so powerful, besides the radiation it gives off, that's why. Give me a second. No. Yeah. All right. Go. Bye. All right, Steph, you're out of here. You're gonna miss the awesome videos, but don't worry, they're on my website, which I'm sure you check on a regular basis.
Your website's awesome.
So,
Which website?
back to this.
No,
It's connected to the school website. I think it's just called Mr. McCoy's Chemistry Class or whatever. It has a link. Anytime we show a video or anytime I show you anything, it's on the website. So you can watch it again.
check out my website.
And there's a link to my YouTube channel, which I have
Oh.
15 subscribers. So I'm getting to be big time here. So, and I don't think any of them are like people I know. I think it's actual students. So, back to this. Bombs, okay? Nuclear bombs, nuclear weapons are so powerful because of this statement right here. So all those scientists that worked on the Manhattan Project to create the bombs that we dropped in Japan, they, have since said that they regret that they did that. It was like a huge advance in science. Everybody got excited, but then they see this here, they weren't quite sure how dangerous and powerful it would be. And it proves, I think, my opinion, it proved that it's too much for humans. Like, we can't handle it, right? Because we're too stupid and we like to destroy each other and the earth. So this is the reason why nuclear weapons are so dangerous and why it's a problem. And everybody's telling everyone else to stop making nuclear weapons, yet they're all making their own nuclear weapons. We're really good at that. So this here is the nucleus. Now, guess what the nucleus is held together with?
Bonds.
Energy. It's called the strong force.
Oh yeah, you told us about that. It's
Right.
like really strong.
That's why it's called the strong force. So the protons and neutrons are really, really, really held together in there. So when you make them come apart, lots of energy is given off. Lots. I can't really put it in perspective except this one little fact I have written down. I might have told you this already. If I'm holding 1 kilogram of uranium, you know how many pounds that is? 2.2. 2.1, 2.2. 2.2 pounds of uranium. It can produce the same amount of energy as 40 million pounds of dynamite. So 2 pounds of uranium, 40 million pounds of dynamite. So you can imagine, if you've ever seen a stick of dynamite or on TV or even in a cartoon or something, they're pretty small. So 40 million pounds would be a lot of those. So this explains a little bit. I'm trying to help you understand. When you mess with the nucleus, you get a lot of energy, which, if it's used for good, okay, not weapons, which is evil, I will say. So used for nuclear power, you can get a lot of electricity out of that, and that's a good thing. But again, with the bombs and the weapons, I kind of wish the world didn't have them, because it is a big deal. As you get older and pay more attention to that stuff, a lot of decisions countries make and politicians make, a lot of it has to do with this nonsense. Who has the keys to the nuclear weapons? So anyways, this is something you need to remember. Mass converted to energy. All nuclear reactions, even all the ones on here, on this sheet you did the other day, mass converted to energy. Anytime you have radiation involved, mass converted to energy. This just happens to be very powerful. Okay, this specific one, fission. Okay, what's the other really powerful one besides fission? Fusion. Where's that occur? On the sun. The sun has a little bit of energy. Okay, so the energy from fusion is even more than fission. So we'll talk about that next. So I'm going to give you one more fission reaction, then I'm going to show you the videos, then we'll talk about fusion, and that'll be it for today. All right, so the other fission reaction we can do is we take plutonium, 239, write this down please, 1/0N, so take a neutron, hit the plutonium, and it splits into barium and strontium, and 13 neutrons. So this is the other fission reaction. Just put it right there. I'll do mine later.
Bro, your back bracket's trash. I'm
Well-
gonna cook you.
Okay. He's beaten me 2 years in a row, so. What are we playing for? Big Mac and Brussels sprouts.
Yeah.
So if I lose, I have to eat a Big Mac. I think I might throw up.
You
if
don't
he-
eat what?
If he loses, he's got to eat Brussels sprouts.
Because he's
Well,
really
that guy
healthy
flies
and
it
Dom
down
is
his
not.
Yeah, Dom is the opposite of that.
Right,
So,
exactly.
Got a picture of Joseph Stalin as his.
If you can't eat a Big Mac, I'm gonna be very upset with you.
the last time I had a
Mustache
Big Mac was
man.
probably like in the 90s.
What's, how come I had you?
I'm serious. I'm dead serious.
It was like this.
All right, listen up. Devin had a good question. He said, "Why is a hydrogen bomb more powerful than a atom bomb?" Right? Is that what you said? Yeah. I actually, kids ask me this a lot, and I don't know how exactly these things are made, so I did look this up last year, and I don't remember all of it off the top of my head, but I do remember that the hydrogen bomb has like 2 processes. I think it does a mini
It's got 2
fusion
stages.
reaction and then a fission reaction. So it's kind of like a double whammy. So it has 2 types of powerful reactions instead of just one type, and I think that's why it's more powerful. But I'd have to look it up again. I forget.
I think
So
the,
it's
the first one going off then sets off
The second one,
it
right,
sets
in the
off
hydrogen
another
bomb.
one, which is
Honestly,
makes
why
it
does
like
it
2
even
bombs.
make one though? Like,
Kind of, right.
Yeah, pretty much.
Yeah.
It's got
It's
it's in
what, is that a
layers.
B or a 13?
BA,
I like World War II.
88, I don't know what you're talking about.
No, the next one.
SR, 13.
Oh.
13. This is 56. SR is, where are we here? 38. All right, so this is another fission reaction. Do you need to memorize every part of the fission reaction? No, just identify it. So, can you identify this as fission? Really, the only 2 reactions you'll ever see with plutonium and uranium are fission. So I guess that's what you need to remember. A couple things before I show you the video here. These fission reactions create what's called a nuclear chain reaction. Who's it going to be here? Sure. What's a chain reaction mean to you?
One event that sets off more events.
Good. One event sets off more events. Very good.
Dominoes.
Yes, domino effect. Right. The chain reaction, here's what happens. Neutron hits plutonium. It splits, produces more neutrons. Guess what these neutrons go on and hit more of?
more those.
More plutonium. And then that produces more neutrons. Guess what those neutrons hit? More plutonium. So it's a bigger and bigger and bigger reaction as it goes. The other thing, the video is going to show that. The other thing I want to write, once this starts, we can't stop it. So fission reactions cannot be stopped, only slowed down. So basically everyone's job in a nuclear power plant is to make sure the reactions, the fission reactions occur slow enough where the power plant doesn't melt down. Because if it melts down, it gets too hot, then radiation gets into the environment. Chernobyl, 3 Mile Island, Fukushima. Sometimes, the one in Japan was a natural disaster and you couldn't do anything about it. But if it's working properly, they try and slow down these neutrons. There's these 2 things called a moderator and a control rod. I thought the video was going to show this. It doesn't, so let me show you real quick, then I'll show you the video. So basically, here's the deal. Here's your reactor core. You have these thin rods called fuel rods. They have uranium in them. This is where the reaction occurs. In between these fuel rods, okay, there's going to be these thicker rods that actually can be brought in and brought out. I don't know exactly how that works. This looks kind of confusing. I should use different color. But in between the thin fuel rods, you have these things called moderators and control rods that absorb or slow down neutrons. The analogy I gave period 2, which I think is a pretty good one, is like a Brita filter. You pour the water in the top, and then it slowly drips through the filter. That filter is kind of like the same thing these control rods and moderators do in a nuclear power plant. If you have a neutron going here, the neutron is going to move quickly, hit these two, and slow down a little bit before it continues through the other fuel rods. So they slow down the flow of the neutrons, like the analogy with the filter. If you pour the water in, you know what I'm talking about. If you've ever seen it, it drips slowly because the filter is filtering. So those things in a power plant are really important, because without the control rod and moderator, these neutrons fly all over the place. All these react too fast, it gets too hot and melts down. So let me show you the video, and then we'll see what we have for time. All right, so lights, please.
How long?
Well, one video is like a minute, the other one's like 4.5. So it will not get you to the end of the period.
Oh man.
All right, so here's the fission reaction first. It's an HD. It's
Whoa.
nice.
Oh, that's crazy.
It is great. It's very crisp.
Nuclear fission is the splitting of a heavy element's nucleus to form two new elements with smaller nuclei. One of the most important fission reactions is that of uranium-235, which is used in nuclear reactors and atomic weapons. The fission of uranium-235 is initiated when a neutron traveling with enough velocity
What are you up
collides with
to?
the uranium-235 nucleus.
What are you up to?
I'm gonna not heat my lunch
Oh,
up.
what are you up to?
Oh, 14,000.
What? What do you do?
Move, stay moving.
I'm at 5,000.
Stay moving. Move,
Alright.
Malake, he'll tell you how I roll. Move, we'll talk. Move, we'll talk.
So when you split the uranium nucleus, you get two smaller ones. Here's the two smaller ones. I think you saw the video there. So it's hit with a neutron, and then it splits. Here's the three neutrons it spews out. They're going to continue on to make that chain reaction.
The collision produces U-236, which immediately splits into two lighter elements, such as krypton-91 and barium-142. The fission event also releases three neutrons and energy. The three neutrons are capable of initiating more fission events if they encounter a uranium-235 nucleus. If a sufficient or critical mass of uranium-235 is present, the reaction becomes self-sustaining, resulting in the release of a massive amounts of energy in the form of heat, light, and ion.
So that's the chain reaction. It's a really good video. It's exactly what happens inside those fuel rods if there's a critical mass. Maybe you've heard that term in movies or on TV or wherever, somewhere. Critical mass means you need a certain amount of uranium for it to be self-sustaining. In other words, if they just put a little bit of uranium in the reactor, shot a neutron at it, it would react and then it would stop. It wouldn't produce enough heat and energy. It wouldn't work. So they need enough, and they, there's people a lot smarter than me that figure that out. They calculate, this is the critical mass, this is how much of this we need, and then they do the reaction safely, hopefully. So this heat energy is what the power plant uses to make electricity. So I'm going to kind of, spoil this. Spoiler alert here. This nuclear power plant video will tell you, but I'm going to jump to the end real quick. Basically, nuclear power plants are built to boil water. That sounds so ridiculous because it's such a complex, expensive, difficult process. But you really use all that heat you just saw there in that chain reaction to boil water. So why do we do it? And remember, there's no pollution, no emissions that are given off. Yes, there's toxic waste, radioactive waste, but if it's contained, that's a big if, I guess, sometimes, but if it's contained, then it doesn't hurt the environment. So those are the reasons that, some positives. Also, I told you the 40 million pounds versus 2 pounds. The amount of electricity we get out of a little bit of uranium is incredible. I mean, you'd have to burn thousands and thousands and thousands and thousands of pounds and liters of oil and coal or wood or whatever to get the same amount of energy. So those are some positives. Negatives, of course, the radioactive waste, the cost, definitely, its difficulty level. But anyways, you're really just boiling water, and you're going to see that. And it's pretty cool how they do it. I think it's pretty cool. So you got about almost 5 minutes here. Yeah.
How are animals thriving?
Because they adapt to it. It just doesn't affect them.
On the show Monster Fish, you ever seen that? He went to
once.
Trumbull and he was fishing and caught catfish.
that's from the radiation.
No,
Yeah.
it's not.
That was-
radiation.
So I thought that was kind of cool. It's kind of true. He said that in 1929.
Nuclear power plants are thermal power stations which generate electrical energy from heat. They consist of numerous buildings and facilities, the most important of which are as follows.
You guys seen that before?
They use those in coal power plants too, don't they?
Different.
It's like same shape.
No. It's like a smokestack for a coal power plant, I think.
You know, it's Boston.
You sure it was a coal, not a nuclear power plant?
Yeah, I was like, yo, what's that? They like, it's a coal power plant. I was like, dope.
Alright, maybe it does look similar. I guess I don't know for sure. So anyways, you guys know what that is? You ever seen The Simpsons?
Yeah.
Did you see that in the beginning of The Simpsons? I'm pretty sure you do.
Lake had on the shirt yesterday.
Yeah, because Homer works in a nuclear power plant, which is hilarious. That's a cooling tower. So a lot of people see these, maybe you don't, but a lot of people, a lot of kids might see those and they'll think nuclear power, oh, that's where all the radiation is. There's no radiation there at all. All it is water. It's cooling. So sometimes there's stuff coming out of those and it looks kind of like whitish.
Steam.
That's steam, right. It's fine. It's not hurting the environment. So I've had arguments with adults who say, oh, I see that stuff coming out of that tower, you know, that's nuclear waste. It's just steam. You know what I'm talking about. Anyways, moving on. So if you see one of those, you see something coming out of it, unless it's a coal plant, I guess it looks similar. I don't
Yeah,
know.
look it up. You
But
look
it
up.
probably wouldn't be white. It'd probably be black coming out of the coal.
Yeah, probably.
Anyways, that's a cooling tower.
They probably have terrible inside of it.
The turbine building houses several turbines as well as the generator necessary for electrical power generation. The containment building where the nuclear reactor is housed is made of meter-thick reinforced concrete.
Alright, so you missed that because Dinkus over here. Just focus, will you? So this is where the nuclear reactor is. This is where the fission reaction occurs. They just said this is made of meter-thick reinforced concrete. Why?
So the nuclear waste doesn't get out.
Nuclear what?
Waste.
Waste.
I thought you said race.
Yes, the radiation doesn't get out of the building. So this is pretty accurate. Wherever the reactor is, it's going to be encased with at least meter thick high density concrete, so the radiation is kept inside.
We should have it lined.
Is there a door to go in there?
Looks like there is, yep.
Why would you want to go in there?
Someone has to go in there.
Die?
No. Wear protective
Just sacrifice yourself to fix them.
You need to stop talking and listen.
Alright.
And yeah, her voice is weird, just deal with it. It's a very good video.
Inside this building, nuclear reactions take place where water is heated up. The cooling tower, which can be as tall as 200 meters, is where hot water is cooled. In order to easily understand the underlying principles, the following is a description of the most important components of a nuclear power plant that uses a pressurized water reactor, PWR. In the reactor pressure vessel, the nuclear reaction and the associated release of thermal energy takes place. In a pressurized water reactor, as in this case, the reactor pressure vessel stands about 12 meters tall. The walls are about 25 centimeters thick. Inside is where the fuel assemblies can be found. In pressurized water reactors, about 150 such assemblies are installed.
That's a
A
fuel
single
rod.
fuel assembly is composed of many fuel rods. A fuel rod is about 5 meters in length and has a diameter of about 23 centimeters.
Yeah, I don't really know exactly, but they're thin. Okay, they're very thin, very long fuel rods, and they stick a whole bunch of them down in the reactor.
The actual nuclear fuel is found inside of each fuel rod. Small nuclear fuel pellets composed of enriched uranium or plutonium make nuclear fission chain reaction possible. In the fission chain reaction, thermal energy is released. Water is needed in order to absorb the thermal energy and keep the chain reaction going. Inside the vessel, the water is heated to over 570 degrees Fahrenheit. The water does not boil, however. since the pressurizer maintains the water pressure constant at around 160 bars. The heated water is eventually pumped to a heat exchanger, also called steam generator.
I'm going to explain this because it might be confusing when she does it, or maybe not. If you got the hot water in here, that's because of the chain reaction. You saw the other video, all the explosions there. So it gives off tons and tons of heat. Water in here gets really, really, really hot, 500 something degrees Fahrenheit. It gets pumped into these little tubes. These are they're called U-tubes. So the water goes through those, and there's more water around them. So there's water from here that goes inside, and then they fill this up with water. So what the hot water in the tubes does is it heats the water around it and boils it. Then they pump the steam out. So she's going to show that. I'm going to skip ahead because it kind of stays on this picture for a while playing music. It doesn't say anything. It's weird.
These are typically in the form of a shell and tube heat exchanger. Hot water flows through the U-tubes, heating up the metal of the pipes so that any water inside the heat exchanger begins to boil.
So yeah, there's water inside the tubes that are wicked hot, but it's radioactive because it's from the reactor. This water on the outside is not radioactive. It's important not to mix that. You'll see why later. So this water boils, so steam is produced, and then the steam is pumped
Steam first drives a high-pressure turbine,
to a turbine.
and then is typically fed to two low-pressure turbines. All of the turbines are connected by a spinning shaft to the electrical generator, which in turn produces AC electricity from the shaft's rotational energy.
So turbines spin, and then that in turn spins a generator, which produces electricity. So turbines are very important for this process. GE makes a lot of turbines. I think they're one of the best in the world at that. So a lot of their turbines, some of them can be used for this. So it produces electricity. So you take heat, boil water, steam from that boiling water turns the turbines to make electricity. It's a very simple process, but you start with a really complex fission reaction, and it produces a lot of heat, so this is very efficient. And then I'm just going to jump ahead here.
Water in the primary circulation system never leaves the containment building. This water is radioactive, since it has been in direct contact with the fuel rods. Water in the secondary circulation system is used to...
So I'm going to stop it. This is the water that's around those pipes, and it gets boiled to make the electricity. This circulates and can cool and be reused. This does not. This stays, it can be reused, but it stays in this containment area because it's radioactive. So it's important not to mix those so you don't have, everything isn't radioactive, just this part. So that's kind of an ingenious thing, I thought. So that's basically how nuclear power plants work. I like talking about it. It's pretty interesting to me, and it's pretty relevant. You know, there's a lot of nuclear power plants. Until we can get better at fusion, which we're going to talk about real quick, this is the best option you have for nuclear. So, last couple minutes, nuclear fusion. Let me get you at least a couple examples here. So fusion. What is fusion? Instead of splitting, that's fission, we put it together. That's fusion. So fusion, first of all, occurs on the sun. Occurs on the sun, and it obviously produces a little bit of energy. It's 95 million miles away, but you can still feel the energy. If you really think about it, that's crazy. Okay? And you can actually get burned, and it's really hot in the summer, for example, and it's so far away. It's kind of cool. So occurs on the sun, and I'm going to give you two of the basic reactions. You need it for your notes, for your homework. If you take H2 over 1 and you combine it with H3 over 1, you will get helium, and a neutron will be kicked out. That's called fusion. You take two hydrogen atoms, their two nuclei, and you force them together under extreme pressure and heat, and you get helium. As a result, you get a lot of energy, even more energy than a fission reaction. Okay, what's hotter, the sun or a nuclear power plant? That's easy. Okay, the sun. So much more powerful. Now the one on the sun isn't exactly like this. There's electrons involved, but this is the gist of it. Hydrogens combine to make helium. The other one you might see is H2 over 1 plus H2 over 1, and then 4 over 2 He. Those two look almost the same. They're a little different, but that's what fusion is. Now, this takes a lot of energy because if you take two nuclei and force them together, they don't want to go together. They want to repel. Why? Why would two nuclei repel? Right, protons and protons, both positive. So it takes a lot of energy to force them together. So this is not very practical in real life for energy because it takes more energy to do this than they get out of it. I have an article here I told you guys about and how in France they are developing a fusion reaction in a plant where they say that they can get more energy out. And there is zero waste, zero pollution. All you get is helium. It's an inert gas. So if we can, master this, we saying humans, the whole world, and use fusion power plants for electricity, I think that would be the answer.
We got
Personally.
moves for days.
Well, we would stop using the earth, so that would be good. Don't forget the worksheet. Don't forget the worksheet. I am after school if you need help.